Okay. In that case, we can take a quick look at round 2 of the business game. So I downloaded the industry report data and did some analysis. All right, so these are the standings in period 1 and period 2. So we see some teams made a lot of practice, look, rack at it. By the way, you guys' names are really lame this year. The rack attack and racket, there's a rack attack and then there's the rack attack. Okay, anyway. Look, rack at it jumped all the way from, what's that, 6th place into 1st. Rack and roll made a big jump. Rack City made a big jump. The Dunder Muffins took a big drop. Rack Attack took a bit of a drop. And Spice Rack took a bit of a drop as well. But the rest were kind of steady. So this shows sales versus price for all of the teams in all of the cities. You can see that there's various strategies going on. Some teams, like the blue squares, had their prices in the 20s all the way up to the, well, and then also in the 40s and the 50s and the 70s. Whereas some teams, all their prices were tightly packed together. Probably a more telling graph is the sales versus price this period versus last period. So the blue circles are this period. The orange squares are last period. So we did not see the huge number of low prices that we did last time. But we also see a distinctly different slope if you were going to fit a line to this. Not that it's necessarily a line. And I will say that there were teams who set their prices at $1 million or whatever in order to not sell anything. I cut those off, basically. So we can see a distinctly different relationship between price and sales this period than last. These are assets, so you can see who made big jumps. Light blue is look rack at it. They made the big jump. The racketeers also increased their assets significantly. They went from 1st to 2nd, but there, as you can see, close behind look rack at it. And also, I'm trying to remember who these guys were. I think this was Rack City. Also saw a big jump in their assets. Nobody lost lots of money, but I mean, that's a pretty low bar, right? I mean, just staying kind of level means you're not making any money at all. Here are stock prices. Again, look rack at it, made a big jump in their stock price, and a fairly big jump for Rack City. Dunder Muffins and Rack Attack took big hits to their stock prices, and everybody else was more or less the same. Okay, this is sales data. So I'm just looking at the bottom line. These are total sales for each company. So some companies sold 0, Rack Attack, and 30 Rack. That could be attributed to the fact that perhaps they had huge back orders. And they decided they better fill their back orders. We see some big numbers as well. The Rack Attack sold 9,200 when we know that they can only make 4,000. And let's look here at look rack at it. They sold over 12,000 units. So even though they're in 1st place, we know what they're going to be doing next period. Dunder Muffins had very low sales. Everybody else was kind of in the ballpark. Just look through the general industry report to see if there's anything noticeable. 30 rec is very low on cash. That's not good for your stock prices, by the way. That's one of the factors that affect stock prices. Finished goods inventory. Everybody is out of inventory except the racketeers. Racketeers are currently in second place. And they have finished goods. Raw material inventory. This is, by the way, finished goods is, I believe, in dollars, not units. The same is true for raw materials. So some companies seem to have a lot of raw materials on hand, probably more than they can use, given that there's only one more period in the practice game. Let's see, net assets. That's kind of the same as the standings. Current stock price. As I look through these stock prices, most of them seem justifiable, except Dunder Muffins have a pretty strong stock price given their standing. And what else was I gonna, there was something else I wanted to point out. Well, while I'm thinking about that, there's a pending insider trade. So Rack City is going to buy 2,000 shares of their own stock. And, oh yeah, we have two pending dividends. Dunder Muffins, $1.25 dividend, and Racketeers, 55-cent dividend. Everybody else seems to be ignoring it. Okay, so Sachil, no major issues last time?
No, there was no issue this time. I contacted the teams who had slightly wrong decisions, but no major issues. Everyone saved their decision form. Correct.
Good. What happened to my screen? Oh. Okay, any questions about the game? So remember, one more period of decisions for the practice round. So if you think you have any great ideas for end game strategies, now might be the time to try them. Okay, I got a few questions about the homework. Not many, which made me a little nervous because I would have thought that would have been fairly challenging. I'm worried that there's answers out there floating around. So I'll warn you, I've made subtle changes to the next homework in case answers to the old ones are floating around. All right, so now the class settles down into more or less its normal form, where I talk about a particular topic for an hour or so, and then basically you can go work in your groups, either on homework or decisions or both. So today's lecture is we're talking about a problem called, sometimes it's called facility locations, depot location, plant location. And the basic problem goes, we're going to talk about a few different problems all related to each other. The basic problem, given a set of nodes which represent customers, so you can think of customers located on a map with demands and known distances between nodes, determine the optimal location for a depot or multiple depots or plants. So in the game, we have 12 sets of markets, and we can build plants, one or more. And when we solve this problem, we assume that the plants have to be located at one of the customer locations. So we're not going to locate plants anywhere on the Cartesian plane, but we're going to limit ourselves to the actual nodes of the network, the cities in the network. And you can also say, if you want to draw lines between all of the nodes, you can locate them on the arcs connecting the nodes. But it turns out that optimal solution is guaranteed to be at the nodes anyway, so you don't have to worry about the arcs either. Right, so the problem is, generally speaking, is to minimize the weighted average distance between depots and customers. And it's the weighted average distance because it's weighted by the demand, right? So in the game, our truck costs involve a price times a distance times the number of units, right? So the number of units would be the weight that you put on the average. So there's kind of a picture of it. We have each circle represents a customer location in the plane. The size of the circle represents the demand that customer has or that market has. And we want to locate the plant, which is the red square, to minimize the sum of the weighted distances, right? So for example, we've got a distance from the plant to this customer, and that distance is weighted by the size of the demand, and then you add them all up. So we haven't done a whole lot with formulations before, but it's really good to understand the way you formulate a mathematical optimization problem. So we're going to declare some indexes. So we're going to index the customers or the cities by I. We're going to index the depots using J. And each city I or each customer I has a demand S sub I. And we have these arcs, the distance arcs. So the distance between city I and city J is Dij. Oops, sorry about that. So then we have this, the distance times the demand, call that Wj, that's the weighted distance, or demand weighted distance. And the cost is, if we're going to locate just one depot, so J is the one city where there's one depot, then this is the cost. This is the weighted distance from the plant in city J to the customer in city I summed over all the customers. Okay, so this is called sometimes the median problem. If it's a single plant we're locating, sometimes you may want to locate more than one plant or one depot. That's called the P-median problem. Okay, so the median problem, locate a single plant. So basically, let's go to an example. So this, finding the cheapest city to locate a plant in does not really even require solver. So we have here a simple formulation, or a simple Excel spreadsheet. So this is just the distance matrix that we've seen before, the distances between different cities. And we need to know what the demand is, right? So obviously this is a shortcoming of this method if you want to use it in practice, because you're never really sure what the demand is going to be. In this case, we're going to assume we know what is the demand in each of the cities, okay? So we can take the demand weighted distance between each city. So, right, you just take the demand times the distance, and that gives you the demand weighted distance. So we have the demand weighted distance. And then if we sum all these up for Chicago, right, that's the total demand weighted distance if we put our plant in Chicago, right? So if our plant is in Chicago, that's the total cost. We just sum up all of the rows, and we can look down, oops, can look down them, and it looks like, according to this analysis, the best city to put a plant in is Nashville, right? So, I mean, there's at least one assumption in here, and the assumption is that these are the demands. If the demands are different, perhaps we get a different answer. Let me make this for example. Suppose I decided to increase the demand in Seattle from 312 to 1,312. Now all the numbers change. And well, now Chicago is the best place to put your depot, right? You can see how that works. We change that back to 300. Now, the next problem we're going to look at is, okay, suppose we already have a plant in Nashville. I thought I fixed it, stuck on it. All right, suppose we have a plant in Nashville and we wanted to see if we wanted to build a second plant, where should we put it, right? So we already know from our Nashville, this is the cost of shipping to each of the other cities if you have a plant in Nashville. So I just copied those numbers here. Right, and I know that if these are the distances from Boston. So I copied those here. And if I had a plant in both Boston and Nashville, then I would ship from whichever one was cheaper, right? So I just have a minimum of these two numbers in each column. I mean, in each, yeah. So these are just the minimums. In other words, what's it going to cost to ship from the cheapest plant? And that tells me what would be the total cost if I had those two plans. So let me add them all up. All right, so that's like 4.2 million. When I had only one plant, it was 4.7 million. Okay. So now I change this around a little bit. But okay, now suppose we can do the same thing, except instead of doing it just for Boston, we can do the same thing for all of the cities kind of at the same time. So in this example, I assumed I have a plant in Denver, right? And then what I do here is I have a min function. So this is the minimum of the cost to supply Chicago. It's the minimum of the supplying it from Salt Lake or from Denver, right? So all of these are the minimum of whatever city and Denver, all right? And then I add them up, and this gives me the cost of having a plant in Denver and a plant in whatever other city I have here. So I look through these and I find the minimum. It says the cheapest one appears to be Atlanta, right? So it's saying if I have a plant in Nashville and I want to build another plant, the cheapest place to build it would be Atlanta. All right, now I kind of did that backwards. So I'm doing the same exact thing again, except now I'm going to assume I have a plant in Nashville, and I do the analysis for all the other plants. Now it says the best place for a second plant is in Salt Lake. All right, so that's not even solver involved there. All right, so the P median problem is we're locating multiple plants, but the way we just did it is we put a plant in what we thought was the best location, and then we put another plant in what's the best location given the first plant. That doesn't necessarily give you the best solution for two plants, right? So this is where it gets a little bit more tricky. So we found the best location for locating one plant. And basically what we did is we tried all n locations and picked the cheapest. If we wanted to find the best two cities for two plants, we'd have to try this many different pairs of locations, somehow enumerate them. And in general, if we were locating 3 depots, it would be n choose 3. possible combinations we'd have to try, find the best. And so obviously, as the number of plants increases, the problem gets tougher. If you're going to take our non-optimization approach and try all combinations, we can see that the number of combinations increases very quickly. So this is just, a table of the n choose p function. And so let's take a number that's not out of line, 100 customers and 10 plants, right? It's like 10 to the power 13 different combinations. This is what's known as combinatorial explosion in some of these optimization problems. And it's one of the things that can make them very hard. However, there are optimization approaches that can solve problems like this reasonably efficiently. And so, for example, we can solve problems with thousands of locations with strong optimization codes. I'm going to skip this one here. And I'm going to talk about solving the p-median problem. So I'm going to give you two different formulations because I think it's worth spending some time on formulations. So the basic decision here is we want to decide whether we open a plant in city I or not. So we're going to have these variables y1 through y12 for our 12 cities. And if we make that equal to 1, that means that there is a plant in city I, and if it's equal to 0, there's no plant in that city. And we have our demand weighted distance coefficients. And this is a formulation that turns out to be not a very good one. The idea is that if y is 0, then 1 minus 0 is 1, and we put this penalty of $1 billion on top of Wij. So if there's no plant in city I, it's super expensive to ship from city I, right? On the other hand, if there is a plant in city I, where's my cursor? If there is a plant that's in city I, this is 1. 1 minus 1 is 0. This $1 billion penalty goes away, and the cost is just Wij like it should be. Okay, so this min function will say we'll ship from the cheapest city, and a city will be really expensive if there's no plant there. And then we just add that up over all of the customers. And then the only other constraint is that we're going to open exactly P plants. And these yi variables are 0 and 1. Okay. Now, what makes this a bad formulation is that it's a nonlinear problem because this min function is not linear, strictly speaking. So when I put this into Excel, actually I get some weird results. Okay. All right, so basically I put it in. So currently I have everything 0, so there's no plants open. So basically you can see that it's costing like over $1 billion to supply every city because everyone is penalized. I just take the minimum of all of these. That's my min function right here. See the min function. And then I add all those up, and this is the total cost. All right, so I put that into Solver. It's pretty easy. And it's nonlinear, so I pick GRG nonlinear. I hit solve. Okay, Solver found an integer solution with intolerance. Okay, so it opened one plant in Washington. Right, now you don't have to be all that smart to figure out that that can't possibly be the right answer. This is one of the things that's annoying about Solver. Let's go back to Solver again. Let's check our tolerance. Our tolerance is pretty low, right? Solve again. Solver found a solution, all constraints and optimality conditions are satisfied. So that's pure BS, right? It's almost obvious that that's incorrect, right? For example, I'm allowed to build 2 plants. There's one in Washington. Oh, let's add one in Seattle. No, where do I want to put it? Let's put one in Denver. And the cost just went down. It's like half as much almost, right? So this is a nonlinear integer programming problem. These are very, very hard problems. And solver is crashing and burning, which doesn't surprise me. But the fact that it doesn't seem to know that it's crashing and burning is a problem, right? Now, oh, I got to go back and introduce this. I'm having trouble here. Give me a second. So we just saw what I would call the bad formulation. But there is a smarter way to do it, and this is it. So we have the same decision variables before. yi equals 1 if a plant is open in city I, 0 otherwise. But now we introduce a new variable. Xij is 1 if city j is served from city I. So this is going to decide from which plant we serve city j. Right? Okay. So our objective function is fairly straightforward. We sum over the wij, xij, right? So this will give us the total demand weighted distance. And then this is sort of the tricky constraint here. Xij has to be less than yij. So xij and yij are both 0, 1 binary variables. But this says that if this is 0, if there's no plant in city I, then xij has to be 0 as well. In other words, we can't serve j from I because there's no plant in I, right? And then the rest of it is pretty much the same. We can open P plants. We have to serve each customer from exactly one city. And we have these binary constraints. All right, so I made a formulation. I'm going to show you another one that's even more clever. So you notice that we have 8 cities here instead of 12. The reason is because solver is limited to a certain number of variables and a certain number of constraints. And with 12 cities, we actually exceed the number of constraints allowed. So I had to cut the problem down. But again, these are basically the distances, demand weighted distances. So these yellow decision variables are the yi's. Do we open a plant in this city or not? And these are the xij decision variables. Do we serve city I from city j or not? If we add up these columns here, that tells me how many plants are open. That's the sum. That should be equal to 2. If we add up these columns, that tells us how many cities are serving each customer, and those should all be equal to 1. And then basically we take this matrix, which says where each city is being served from, and we sum product it with the demand weighted distances, and that gives us the total cost, which is right here. And what's nice about this formulation is it's linear, so we can use simplex LP. But you see, we got a huge bunch of constraints here. And most of these constraints are the xij less than or equal to the yi's, right? So we have this column is less than or equal to this column. And we have this column is less than or equal to this column. Dot, dot, dot. All of these columns are less than or equal to this column, right? And so all of those constraints are why I had to limit it to 8 cities. Nevertheless, since it's a linear problem, it solves pretty quickly and gives us 438. Oh, wait, what is that? Yeah, 4.3 million. This was the same, the bad formulation we used. Right, and it gave us a ridiculous solution. So now this is the same formulation. And remember what the problem is. Let me just go back. The problem are these constraints here. The xij are less than or equal to the yi's for all I and all j. That's a whole bunch of constraints there. So I believe it was Thiel, if I'm not mistaken, who came up with this clever solution to that problem. Right, so the idea is there has to be a 1 for this city, right? So here we got a 1 here and a 1 here. So it says we have a plant in Atlanta and Salt Lake. So that means that for all these other cities, all of these guys have to be zeros, right? However, only the variables in these 2 rows are allowed to be 1s because those are the 2 plants that are open. So the suggestion is you add these all up, right? And you say that this sum divided by 12 has to be less than this value here. So for example, not all of the guys in this row are 1s. So when I add them up and divide by 12, I get a number bigger than 0, but less than 1. But that's fine, right? It's just saying I have some 1s in this column, and that's what I'm trying to do. Right, so now I just have the constraints that these 2, that this column has to be less than or equal to this column. That makes many fewer constraints, and it makes it easier to put in the solver, and it's still a linear program, a linear problem, so I can use simplex. Now I can solve all 12 cities. Okay, notice that it gave me a solution of 2.8 million. Now I could say, what if I want to open 4 plants? So I'm going to now allow 4 plants to be open. Right? Let's try solving it again. It's going to take a while, but it should solve. Okay, so now it's 1.5 million. Okay. So notice that all the costs are transportation costs in this problem, right? So it makes sense that if I open more plants, I could save some money. So here's the question. What cost am I not including, right? Is it always true that I should just open more plants? Is anybody listening? Why wouldn't I just open 12 plants and my transportation costs are really low, right?
If the expected, increase in profit from opening the plant is less than the expected long-term cost of opening the new plant.
Oh, So you're saying plants cost money? Is that what you're trying to tell me?
Yeah.
Right. So I did not include that, did I? I didn't include that. Which brings me to the next problem. Which is called the Uncapacitated Fixed Charge Facility Location Program. Okay, so basically we're going to add a cost for every plant. We're going to assume that it costs money to open a plant, and we're going to let the number of plants be a decision variable. But it's uncapacitated, and what this means is that all these plants or depots have unlimited capacity, which you may think is not realistic, and you'd probably be right. You may also suspect that we're going to fix that one in a minute too, and we are. But now let's just add on the fixed charge for a plant. All right, so the example, this formulation is exactly the same as the last, except we added on a cost of C dollars for every plant we open, right? Remember, YI is 0 if we don't open it, it's 1 if we do. And then we had this as an equal sign before, we're making it less than or equal. So you can put a limit on the number of plants if you want. Or you could set this all the way to 12 and allow for the possibility of opening a plant in every city, but now we got to pay for every plant. And aside from that, the problem is the same as the last one. Okay. So the problem is pretty much the same as before, except now I have this cost here, right? So this is the total number of plants that I've opened, and I multiply that by $140,000, the cost of a plant. Then I add together the transportation cost and the plant cost to get the total cost. All right? And just to look at the transportation cost, it's the weighted distance, right? The demand times the distance times 0.005 per unit per mile. And then I multiply by 12 because it's 12 periods, right? So, you know, you're going to be, the amount it's going to cost you is over 12 periods of the problem. The plant you only have to pay for once. So that's why I put that 12 in there. And kind of a good, easy way to represent the constraints are here, right? So all of the yellow ones, there are binary constraints on, and the blue ones, there's binary constraints. This says that this has to be equal to that. In other words, this has to be equal to that. That means that each city is served from exactly one plant. And then this has to be less than or equal to that. That's that thing that guarantees that if the YIs are 0, then the XIJs with the same I are also 0. Okay. So wait a minute. So we can do solver. So again, everything in this model is linear. And so we can hit solve. And it gives a solution. All right. So in this case, it says open one plant in Nashville. Okay. Now we can play around with this a little bit. Suppose that transportation was more expensive. Suppose instead of $0.005 per unit per mile, it was 10 times more expensive. Now what do you think will happen? So shipping is way more expensive. There's probably more benefit to have plants scattered throughout the country. And now we're going to open 4 plants. out of curiosity, where are they? Miami, Washington, Nashville, and Salt Lake City. Okay. And also, if I were to change the demand around, I could get different solutions as well. Right? Now, again, we're assuming that I have unlimited capacity, right? So I may be sending more than 4,000 units from one plant in this problem. Right, capacitated facility location problem. Now each depot has a capacity, or each plant has a capacity. We're going to assume it's 4,000 units. You cannot ship more than 4,000 units from a plant. Okay, so now we need a slightly different formulation. Now Xij is going to be the fraction of the demand in city J that is served from city I. So because of the capacity restriction on each plant, we may not be able to supply all of the units to a city from one plant. We may need multiple plants. Right, so now this is a real number between 0 and 1. Yj is the same, except there should be an I. I don't know why there's a J there. It should be an I. And this should be a J. I changed the stupid distances around. Demand in city J, distance, cost of opening a plant, and now we have a capacity of each plant. Right? So the formulation is slightly different. And we have the fraction of demand supplied from the plant, multiplied by the distance and by the supply and by the demand, plus the plant cost. The rest of this constraint is the same. If we have no plant, then this has to be 0. When we add up over all of the plants, so we're summing over the plants here, summing over the plants, how much is sent to city J? That has to be equal to the demand in city J. And the amount, if we sum over the plants, if we sum over the cities, this is the amount sent to each city. And when we sum over all the cities, that has to be less than the capacity of the plant. Right? So we're just starting to see these formulations. You may not be getting them the first time, but eventually I think it'll make sense. Okay, so this is going to look fairly similar. Okay, so we have, these are just the distances. Oops, that's the wrong one, sorry. Go to version 2 here, not version 1. Those are the old versions. Okay, so we have our distances. This is our assumed demand. These are our plant open decisions. That's the sum. It means that's the total number of plants open. These are the fractions of demand served from each plant, right? These are the same constraints that enforce that if yi is 0, xij has to be 0. And then we have down here, if I take the fraction supplied, for example, 61% of the units that go to Chicago come from Atlanta, 38 from Salt Lake. I take this matrix and I basically sum product it with the demand to get these rows. And this tells me the total amount that's supplied from each plant. And I add them up across all the cities. This is the total amount supplied from all of the plants, and it has to be less than 4,000. So that's the new constraint added on. Okay, so it's a slightly different formulation. Again, the beauty of this formulation is everything is linear, so I can use simplex LP. Solve it. In this case, it says to open 2 plants in Atlanta and Salt Lake. Again, I could probably mess around. Let's make the demand in San Francisco increase by 1,000 and the demand in LA increase by 2,000. Just for the heck of it. And run it again. Okay, so now it opened 3 plants where Los Angeles, Denver, and Atlanta. Okay. So this is a pretty useful model. The only problem is that you're not really sure what the demand is going to be, right? However, you could maybe make up some guesses, right? Create some scenarios of demands and solve the problem for each one of those scenarios to see where the plants are recommended. And if you look at a few of them, maybe it'll give you a really good idea where the plants should be. All right. So I'm going to kind of change the direction of the lecture a little bit. I've kind of taken these depot location problems about as far as they can go. All right, so this is a slightly different problem. So the problem we've been solving all along, we're assuming that the plant has to be located in one of the cities on the map. And technically, you probably could build a plant anywhere on the map you wanted to, all right? So suppose we allowed that to happen, all right? So now we do not have to put the plant at a city. So each city I has a demand, not facility. There are end customers. Facility may be located anywhere in the plane. And we're going to use the distance from the facility to the customer, and we're going to use Euclidean distance. And we're going to minimize the total cost for distance times weight, or distance times demand. And this is known as the Weber problem. Actually, one of the, if not the oldest facility location problem, and even Fermat discussed this problem in the 1600s. Okay, suppose I indexes the many customers we have with X and Y coordinates, AI and BI, and X and Y, those are the locations of the facility. So these are the decision variables. We're trying to decide the location of the facility, decide what is X and Y. And we want to minimize the distance from the plant to the customer. So this is the square root of the sum of squares. This is the distance from the plant to customer I multiplied by the demand and then summed up over all of the customers. We want to minimize that function. So there are no constraints actually, but this is a nonlinear problem, as you can see from the squares and the square roots. So you kind of look at this picture and you say, well, how come the answer is not the center of mass of the system, right? So suppose I was solving this problem, and you'll note this is not the same problem as the one I just said. And what's different about it is here I have a square root, right? here, I don't have the square roots. I'm minimizing the squared distances, the squared weighted distances. Now this problem is easy. I can simply take partial derivatives, set them equal to 0, and solve for the solution. And the solution I get is, in fact, the center of mass. So, you know, if you were tempted to say that the solution is the center of mass, well, the center of mass is a solution to a different problem, minimizing the squared distances. But that's not the problem. I want to minimize the actual weighted distance with the square root sign there. Okay, so the problem we're trying to solve, the Weber problem, has the square root up here. And you can try taking the partial derivatives and setting them equal to 0 and solving, but good luck with that. One way to look at it is if I had a one-dimensional Weber problem. So imagine all of the customers were on a straight line. And I wanted to decide where to put my plant, right? What makes it a little bit, okay, so if you look at it this way, you say, this is what I want to minimize because I only have one dimension, I'm on a line. So is that the same as minimizing this? The answer is it isn't, because you got to remember the absolute value part, right? So minimizing this is the same as minimizing this. And the partial derivative of this is not known because it's not continuous. All right, so then the question becomes, if you imagine that, you know, your cities are all located on a straight line, where should you put your plant? That's one of the homework problems. Okay, so that's the end of my lecture, except I want to look at the homework problems briefly here. Okay, we have 5 problems. So these are kind of like stepping through what we did in the example problems. All right, so where would you put one plant? Given these demands, given a plant from part A, where would you put your next plant? Okay, suppose you can open a plant in any 2 cities you want. Which 2 cities should you use? And in part B, suppose it costs you $100,000 to open a plant. Now, where would you build plants? And we also have to decide how many lines to build in those plants. All right, problem 3 involves warehouses. So this was not an issue in the practice round, but it will be in the game. So basically, this is a fairly easy problem. But you're going to put a warehouse somewhere, and then you're going to figure out how much money that's going to save you over, say, 9 periods of the game. Oh, I missed an example. Okay, let me go back and do one more example. Actually, I have a couple more examples. Shoot. All right, you can, the Weber problem is easily solved in Solver. Hopefully you can see this, right? So these are the locations, XY coordinates of the cities. This is the demand in each city. These are the decision variables, X and Y coordinates of my plant. And then this is my objective function. So given locations of the location of the plants, I can compute the demand weighted distance to each city, and I added these up to get my objective function. So again, there's no constraints here. There's just the objective function and the X and Y location of the city. Now it is a nonlinear problem, right? You got squared terms, you got a square root term, so you got to use GRG nonlinear. But even, this is an easy problem for GRG nonlinear. Now what I have here is a 2-depot Weber problem. This is kind of interesting. So again, I have the city coordinates and the demand. But now I get to put 2 depots. So this is the location of one depot, location of another depot. And you always have to, when you start, right, you have to put something in for the decision variables, right? So basically what we do, we find the demand weighted distance from each city to depot 1, demand weighted distance to depot 2, and then we use whichever depot is closest, right? We take the minimum and then add these up, and that's our objective function, right? So this turns out to be a somewhat interesting problem. Okay, hit solver. Solve. Ah, screwed up. Let me try that again. Solver. In the way it's usually defaulted. And it gives me this objective function, 34,000. And it puts both plants at the same location, right? So you don't have to be too smart to figure out that can't possibly be right, right? So then you may try something else. Let's try a different initial solution. Okay, do that again. Let's start the problem off somewhere else. Okay, now we got that solution. And let's try here. All right, so the point is, depending on where I started, I got different solutions, right? Now, remember on the last week, we had the problem that was like sine waves, they had multiple peaks in it, right? And we said that was a non-convex problem. And that's exactly what's going on here too. This is a non-convex problem. If we started off at 0, 0, 0, 0, we get one solution. And if we started off somewhere else, we get a different solution. This is a non-convex problem. So where you end up depends on where you start, basically. So in solver, so I'll put that back to 0, 0, 0, 0. In solver, for the GRG nonlinear, so you click on the GRG nonlinear options, there's something called use multi-start. So what this will do is it will pick something like 100 random starting positions, right? So the initial X and Y locations of the 2 depots will be generated randomly. And then it'll climb the hill to the local optimum. And then from each of those 100 starting positions, it will find the best solution, right? And so this one is going to be way more reliable. And you can see that it found these locations for the depots, which is probably, I can believe that anyways, as being pretty good. All right, so those were the examples I didn't cover. Probably worth it because they're related to the last 2 homework problems. All right, so I've been going on for an hour. That's probably enough. Does anybody have any questions? Many people, ultimately 50 people showed up. I'm kind of curious who didn't. Okay, so Sachil, the next round of decisions are due